Hello friends, welcome you all to the 20th session of ARM based development. So in this lecture, starting from now, we will be looking at things which are outside the processor. Okay, so today we will be starting with coprocessor. Okay, then I will give you some introduction about floating point format, then followed by a vector floating point processor. So up to this point, the number of units that we have covered so far talked about what is inside the ARM processor core. Okay, so just to give you a flavor of this, one second, sorry. Okay, so let me tell you what we have seen so far. This is ARM core. So we talked about, we are talking about a system with the ARM based processor, Okay, so in the SoC, the system on a chip, what we are seeing is what happens inside ARM core, how does it execute in different instructions, and how does it talk to different kind of memory, how it reads the instruction from there and how it writes back. So it was maximum maybe the instructions related to some memory in connections, and then whatever is being executed inside the core. Now onwards we are going to look around the ARM core. Okay, having completed the instruction set including the thumb state and ARM state, and then handling of interrupt where peripherals were connected, and then we have touched upon how ARM processor handles the interrupts. Now we are looking at the processors or cores which are outside the ARM. One is coprocessor. Okay, so the naming itself means that it is a subset, or not even a subset, it is a add-on to the ARM processor. Okay, that's why it's called coprocessor. It's not a main processor, but it's an add-on to ARM. So it is also inside the SoC. Okay, where ARM core is inside, and then memory, maybe some cache or whatever, and then there are some buses which we will be talking about, ARM specific buses which connect the different peripherals and then coprocessor. Now our interest is going to be, if suppose we want to expand the functionality of ARM core beyond what it supports. So that ARM supports 2's complement integers, right? So both signed and unsigned. Now what if it is for the ARM SoC that you are using it, and the application is for some scientific application, and where you will be using a floating point operations. Okay, floating point. I will be talking about this floating point arithmetic as well as the format. So in case if we want to expand the functionality of ARM, we could do it by adding those features into the ARM core, or it could be done by adding that specific application specific features into some other processor which runs along with the ARM core. Okay, so you may wonder why are we doing it? Because in a design, in a system design, we may not need a coprocessor always. We might be happy with only having an ARM core along with the peripherals and the memory. So if suppose the coprocessor is also built into the ARM core, all the functionalities of coprocessor like floating point support, then it will be unnecessarily increasing the size and power consumption and complexity of the chip in terms of area, in terms of power consumption. So we do not want a functionality into the inside the processor where it is not required. So that is the reason why a special functions like a DSP, digital signal processing, or a specific floating point processing, or network processors, it could be any of the specialized functions which are very specific to some applications where this ARM based system is going to be used for. Okay, in that case, we can the user as a user, the system designers may decide to have coprocessors which are specific to those functionalities and then add it with the ARM core. So it effectively enhances the functionality of the ARM, at the same time preserves the simplicity of a single core. Okay, so that is the intent of going in for coprocessor. So we in this lecture we will talk about ARM coprocessor interface. Okay, and then in the next lecture I will talk about the instructions which are related to coprocessor. Then I will explain you about floating point format, followed by a lecture giving inside what is inside a vector floating point processor. So typically we start with how a coprocessor is interfaced with the ARM, and then what are the instructions supported by ARM, then how it is implemented to support a floating point arithmetic operations. Okay, so this will give you a complete picture of what is a coprocessor all about and what is the use of them and how is it implemented in the ARM processor. Okay, along with ARM processor. Okay. Okay. Now let us see. Let me take the pen back. So these are the topics which are going to be covered today. Why we need coprocessor, and then how ARM and coprocessors are connected to each other. What are their interface and what are their signals they exchange between them, and then we will touch upon pipelining in the ARM, and then how does it connect? How is it connected to the coprocessor, and whether does it have a pipeline, and those details will be covering today. Okay, I told you about why we need coprocessor. So it is to enhance a functionality. So additional instructions, specialized additional instructions can be added using coprocessors to extend the functionality. Okay, it could be DSP or a floating point operations. Now, when I say we are adding more instructions, you know that ARM has a 32-bit wide instruction set, right? So we are not how many instructions could be there using those 32-bit combinations. There could be a 2 power 32 instructions. But does ARM have that many instructions? It doesn't. So it has some set of instructions. I don't top of the mind. I don't recall how many instructions are supported in 7. Maybe 30-40 instructions, because there are so many varieties to that, because conditional stacks may be different, and then you will have different, whether it could be with the X option or without the X option. So there are multiple combinations are possible, but even if you support all of them, it will not be at anywhere close to the number of options we have with it to 32-bit wide instructions. So the instruction formats which are not used by ARM. Okay, so you know that ARM opcode, and then we have talked about every instruction, how they are dividing this particular ARM 32-bit instruction into multiple fields and how it is used. So we know those things inside. So the combinations which are not supported, which are not used by ARM, okay, they are going to be the gaps in the instructions of ARM are going to be used by the coprocessor instructions. Okay, so the bit combinations of coprocessor instructions will be different from what is currently which is being supported by ARM. Okay, in supporting the ARM instructions. So the coprocessor instructions will be a different combinations of bit patterns. Okay, now this is what we are going to be using for supporting different functionalities. So in this talk we are not going to talk about how is it inside the coprocessor instruction. Only thing what you should remember is that this coprocessor instruction combination is different from what ARM has already reserved it for its own instructions. Okay, that is enough. And then we will see how it is supported in terms of connecting a coprocessor with the ARM, and what are the other signals which are getting exchanged between ARM core and the coprocessor. Then we will talk about what are the instructions which are supported in coprocessors, and then how different coprocessors can use them to support their functionalities. Okay, different functionalities. So one thing we have to remember, the coprocessor instructions are also 32-bit wide. Okay, that's what I am saying. So then you may wonder, is there a thumb state for a coprocessor, right? Because we know that ARM core has its own thumb state. That means it has got a 16-bit wide instruction set format, right? So which is different. Okay, if it is a ARM is in the thumb state, then it will be executing 16-bit instructions. But does the coprocessor also have thumb state? It doesn't. Okay, so if ARM processor is in thumb state, okay, suppose, then we cannot have any coprocessor instruction being used. Okay, so one thing what you should remember is the coprocessor instructions are all 32-bit wide. So only when ARM is in not in thumb state and it is in ARM state, then a coprocessor instruction can be there. Now I will give you an example. Okay, suppose you have the typical add S instruction. Okay, R1, R2, R3. Is this a coprocessor instruction or is it a normal ARM instruction? It is a normal ARM instruction, and this is a 32-bit wide instruction because there are 3 operands in it. Okay, and we mentioned also about S option. So that means this is a 32-bit instruction. Okay, assume it is in some location in memory, and then we give another format. Okay, maybe F add. Okay, floating point add. Assume it could be different for different processor. So F add some registers. Okay, it could be RF1. Okay, floating point. Okay, registers RF2. No, I am just giving you some syntax because this syntax is not specific to a particular processor. It could be different. So and then followed by maybe a subtract R1, R2. So you are writing an assembly program like this. Okay. Now every instruction is going to take 4 bytes length. So if this is starting at 100, address 100, this instruction will be at 104, and this will be at 108. Now this whatever instruction, okay, that I have written here is something specific to a coprocessor, maybe a floating point. Okay, the format may be unique to a particular processor, so we are not bothered about that, but it is nothing to do with the ARM instruction. Okay friends, there was a technical issue, so hopefully you should be able to see this what I have written. See, I am explaining you how does a coprocessor instruction, okay, gets embedded into a typical ARM core, ARM instructions. So when we have a coprocessor support in the system, okay, we have an SoC, okay, ARM core is there, assume that ARM core is there, and then there is one coprocessor which is maybe a floating point coprocessor, which also is there in the SoC. Okay. Now you can write code by embedding the floating point instruction in between the ARM instructions. So and they are all 32-bit wide, both ARM instructions as well as the floating point instructions, which happens to be a coprocessor instruction. So they all come through the same instruction pipeline, and they get into the pipeline of the ARM core as well as a coprocessor. In our case, it's a floating point processor, which is always looking at the data bus. Okay, and then it is in sync with the ARM core, and then it is also getting this instruction. So when this instruction, when the ARM processor decodes this, it will realize that okay, I have got a floating point operation which is not what I could execute. If there is a coprocessor which supports this particular instruction, then it might pick the instruction to execute. So when this particular instruction comes into the execute stage, it looks for a coprocessor whether is it ready to take this instruction or not. If there is a coprocessor, suppose there is a floating point coprocessor which has it is also reading all the instructions which are read by the ARM core. So it will know that I have an instruction for my, so it will start executing it. So it will execute it only when that particular instruction reaches the execute stage of the ARM processor. So there are two pipelines. One is inside the floating point processor, and ARM anyway has a pipeline. So these instructions flow through all these instructions. Okay, all these instructions flow through both the pipelines, and then if the particular coprocessor instruction what ARM encounters is also supported by a coprocessor which is in the system, then that floating point processor or coprocessor picks up that instruction and starts executing it and informs the ARM that okay, I will take care of that. So this is the kind of a handshake which we will be covering now. Okay, just want to give you a overview where the whole thing is working. So ARM instructions are all there, and then in between the floating point instructions are embedded into them. So they also occupy a 32-bit wide instruction, but they are different format than what typical ARM instructions follow. So ARM processor knows that okay, it is not my instruction, so it will look for any takers in the system. So there could be a floating point coprocessor, and there could be a DSP, another DSP processor. Okay, so you may have an instruction from a floating point operation, and then maybe a filter operation. Okay, filter some register name. So this instruction also can be there. So this will be picked up by the floating point processor, and then the filter instruction may be picked up by the DSP processor. So now you may wonder how. So the instruction fetching and decoding is happening on instruction fetching is done by the ARM core, whereas what is being fetched is all looked by the other cores also, other core processors which are looking into the database. They also keep their pipeline, they also have a pipeline similar to ARM core, 3-stage pipeline, and they keep filling the instructions what they see while the processor ARM is accessing the instructions from the memory. So typically coprocessors also run at the same main clock as that of ARM core, and they are in sync with the ARM's pipeline. Have this background, okay? So this will help you to understand the rest of the topic. Okay. Okay. Let us go into the details. Sorry. One second. Okay, friends. Let us carry forward. There are separate processing units that are tightly coupled to ARM processor. Okay. It could be a DSP processor, or it could be a floating point operation processor, or a network processor. It could be anything. The typical, what does a coprocessor contain? It contains an instruction pipeline which is following the ARM pipeline. Okay, it follows the ARM pipeline in lockstep. That means every clock the pipeline in the coprocessor also does the same thing that ARM core does. So ARM might execute its own instruction. Okay, it has to, of course. Then what does the coprocessor do with the ARM instruction? It ignores that. Similarly, when ARM encounters a coprocessor instruction, it knows that okay, it cannot be executed by ARM itself. So when that particular coprocessor instruction reaches the execute stage, then it controls. Now it asks for any coprocessor who is willing to take that instruction. Then it will allow that instruction to be executed by the coprocessor. So and ARM ignores that. So typically the instruction pipeline is there are one in ARM and then there will be instruction pipeline in each of the coprocessors and they all go in lockstep. Okay. So a coprocessor has its own instruction decoding logic. So it can understand its own instruction, but it will not understand the ARM processor instruction. So it will know that okay, it is the ARM instruction, so it will ignore it. Okay, that much of knowledge it will have, and then it has a handshake logic to communicate with the ARM. So what I mean by handshake logic, some set of signals. Okay, I will tell you what are the signals that it uses to talk to the ARM core, and then the coprocessor also has a set of register bank. It has got its own registers inside. Okay, and a special processing logic with its own data path. So we have seen ARM's data path, right? How instruction comes through, goes through what all the stages it goes through and how the registers are accessed, how many register ports, all those things we saw in the data path of ARM. So similar to that, there is a separate data path inside the coprocessor. So that only can use the coprocessor instructions to work with its own registers and does the separate job, which is scientific operation mostly. Okay, so this set of things gives you a flavor of how a coprocessor behaves. So coprocessor is an add-on. It sits outside the ARM core. In the sense, in the SOC, ARM will be there, and then coprocessor will be there, and then I will tell you how they are connected to each other. Okay, and then we will see that the coprocessors have its own instruction pipeline and its own decoding logic, and they talk to the ARM core using some signal, and ARM also looks at those signals, and then the coprocessor has its own register bank and its own data path. Okay, this you should have in the back of the mind, then only you will be able to appreciate how does the coprocessor work. Okay, I will give you more and more. When we go into the details of the signals and how they talk to each other, you will understand how these things all come together to make this coprocessor function properly. So a coprocessor is connected to the same data and control buses of ARM. Okay, please remember it is connected to the data and control buses and not to the address bus. Okay, that is very, very important. Address bus is not connected to the coprocessor. Why? The address generation, okay, and instruction fetching is handled by whom? It is done by ARM. Okay, so instruction fetching is done by ARM, but while the ARM is fetching the instruction, it is also read by coprocessors. Okay, so ARM issues the memory read to read the instruction, okay, from memory. So this is the address bus, and then there is a data bus, okay, which is also connected to the coprocessors. So and then the control signal is also there. There is a control signal between them, ARM and coprocessor. So the coprocessor is continuously monitoring the transaction happening on the bus, and then it knows where the instructions are getting, when the instructions are getting fetched, and it takes that instructions also into it. So it will go through its own pipeline. Why the same instruction is going through the ARM's pipeline? Okay. Now at some particular point, that is a decode stage, both the ARM as well as the coprocessor, they realize that a particular instruction has come which is meant for this guy and it is not for ARM. Then when that particular instruction reaches the execute stage, coprocessor takes on the control of executing that instruction and ARM ignores it. As soon as it knows that, coprocessor informs that I am going to take this instruction, you don't worry about it. Then coprocessor executes it and ARM ignores that. Then you may wonder what does it do? It will go with the next instruction. Okay, it will keep. So it will ignore. Okay, this instruction is a special instruction. It doesn't ARM doesn't even know whether it is going to take 2 cycles or 10 cycles or 50 cycles. It doesn't know. So it is totally implemented by the coprocessor. So it could be in some internal e power x operation which may take a longer time. So ARM will carry on with its own job. So the coprocessor will perform the e power x operation and then store it in its own internal register. So that is what happens. So I am telling this background again and again because you have to remember this to understand how the instructions get exchanged between them. So it is coprocessor connected to both. Coprocessor tracks the pipeline of the ARM processor. Okay, this means that the coprocessor also decodes the ARM instructions in the instruction stream. So coprocessor also should know whether it is the instruction is meant for its own execution or it is for ARM or for some other coprocessor. See, coprocessor is one entity there. There may be another set of some few coprocessors in the system. So, but what particular coprocessor will look for its own instruction. And then you may wonder how does it know which instruction belongs to itself. I will tell you that. Okay, that is there will be a coprocessor ID which will indicate to the coprocessor that it belongs to it. So it executes those that coprocessor supports, ignores the instructions that are meant for ARM processor or other coprocessors. Okay, so it will just ignore and then carry on with the pipelining, similar to what ARM does. Each instruction progresses down both the ARM and coprocessor pipeline at the same time. Please remember they are at the same clock. The M clock, which is the main clock, which is connected to both the coprocessor as well as ARM. So they run together and the instructions go through the different stages of the pipeline together. Okay, but physically they are in a different places. They are in fact, they are running in parallel. They are having a different hardware and they all look at the same instruction and they execute it together. Okay, if a particular instruction belongs to coprocessor, it will execute, otherwise it will ignore it. So the execution of instruction is shared between the core and the coprocessor. So execution of instructions, that means what? ARM instructions are executed by ARM core, and if any coprocessor instruction comes, that will be executed by the coprocessor. So they are actually running in parallel. They are in parallel. They are in sync. That means each, when a particular instruction is in fetch mode in ARM core, the same will be in this fetch stage of the coprocessor. The same instruction. Okay. So this is the basic fundamental of how a coprocessor is connected to the ARM core and how they function. Good. I hope this is clear to you. Now I will introduce you to the different signals and interfaces which will make sense now. So this is the diagram. See, there are n number of coprocessors, okay, but maximum is 16. Okay, ARM7 supports 16 coprocessors. So, but I have given you a sample where n number of processors are there. ARM core is here and coprocessors are there. They are all inside one SoC. Please remember that. Okay, they are not in a outside the chip or something. They are all in the same SoC where the ARM core is. Okay, and there are control signals which are connected to both ARM as well as to the coprocessors. Which are the control signals? I will explain in the next slide. But control signals are connected to both of them, and the data bus is also connected to both the processors. Okay, so ARM is also reading an instruction, and at the same time the same instruction will go into the all the coprocessors. Okay, please remember, if there are 3 right now, let us assume that there are 3 coprocessors. We will call this as a 3 coprocessor 3. Then when an instruction is fetched, it is going into ARM core as well as to all the coprocessors. And if it happens to be a coprocessor instruction, it may See, coprocessor, any instruction is 32-bit here, and there is a coprocessor ID. Okay, assume that this is the field coprocessor ID, CPID I call them. If it happens to be a 3, one instruction with a CPID 3 comes. Now this guy will pick the instruction, and ARM will ignore it, and other cores will ignore that, and it will execute it. Now next, immediately after that, there is another 32-bit instruction, but it happens to be a coprocessor instruction, but with the CPID of 2. Then this processor will take it, the other coprocessor and ARM core will ignore it. So that's the way the instructions get into the processors and they talk to each other. Now, how does ARM know a particular instruction is taken over by a particular coprocessor or not? These are the signals. Okay, let me explain these signals now. In detail. I will. Okay, see here. This is the NCPI. Okay, that is the ARM core has recognized that a particular instruction that it has seen is a coprocessor instruction. It's not an ARM instruction. Then it will make this signal low. Okay, because NCPI, so coprocessor instruction. So it will send it to all the processors. All the coprocessors are reading this NCPI line. So they will all come to know that, hey, there is one instruction which the ARM core has recognized that it will be a coprocessor instruction. Now, when will this signal be generated? Only when this coprocessor instruction has reached the execute stage. See, remember, a coprocessor instruction will first come into this fetch stage, and then during the decode stage, when the coprocessor instruction moves into the decode stage, the ARM core recognizes that, oh, it is a coprocessor instruction, it is not my instruction. So, and then if it happens to enter the execute stage, why do I say if it happens to execute? There are some possibility that the coprocessor may never come to the execute stage because the previous stage was a jump instruction, branch instruction. Then this branch would have taken the control to some other instruction and leaving this coprocessor instruction at the decode stage itself. It is not executed. So the decision of a particular particular coprocessor instruction getting executed is actually in the hands of the code which is being executed by the ARM. So if it has executed a branch instruction just prior to the coprocessor instruction, the control would have gone somewhere else and the coprocessor instruction wouldn't have entered the execute stage. In that case, the NCPI will not happen. Okay. Then these coprocessors, which are suppose the coprocessor instruction ID was 2, and this would have picked it up, but now it sees that NCPI is not becoming a low. That means the ARM has decided to ignore, decided not to execute it, not to be executed by any of the coprocessor also, because ARM may not execute it, and it will not ask others also to execute if a control takes it somewhere. You may wonder why is it implemented this way. See, you might have written a code if I is equal to some integer equal to 1, then you do a floating point add, f add. If it is not equal to 1, you will continue with some other instruction, ARM instruction or whatever it is. You don't want this f add to be done. So we are mixing the floating point instruction along with the normal control ARM instruction. So in that case, you should not allow the coprocessor also to execute this instruction. So that is the reason the processor decides that this instruction is not to be executed and it will not raise this NCPI signal. Then what happens? The coprocessor ignores it. Even though it belongs to its own, it will ignore it. Okay. So remember this logic. NCPI is generated when that particular signal reaches the execute state. And one more possibility is that you are adding f add, you want to do a f add EQ, suppose. That means what? If you have a 0 flag in the ARM core equal to 0, equal means it is equal to 1, then we want this instruction to be executed, otherwise we don't want. So that ARM core decides whether to execute a particular instruction or not, including the floating point. So that is control is with ARM. So that's why main control processor is ARM. They are all coprocessors. They will do the job that ARM expects them to do. but they know how to do the job. Okay, ARM doesn't know, but ARM controls what this coprocessor should know, should do, and when they should do. So that is controlled by the NCPI signal. Okay. Now, okay, it will. Suppose you assume an instruction, a coprocessor instruction has come into the ARM core and it has to be executed. It has reached the execute stage of the pipeline. Very good. Now ARM cannot do anything with the coprocessor instruction. Only it can do is it can inform the other coprocessors in the system. Please remember, ARM doesn't even know the existence of these coprocessors. Okay, there is no way of ARM knowing it. It just looks at the instruction and says that okay, it is not for me. It just informs it raises the signal and then waits for anybody taking this instruction or not. Now how does it know? There are two signals for it. Okay, what is that? Coprocessor A means coprocessor absent signal and coprocessor busy signal. I will explain this here itself because the picture is there and you will be able to understand the whole flow of it. Then we will go through the slides to understand the exact sequence. Okay. Now after this NCPI is given, it is waiting for these two inputs, okay, to come from any of the takers if they are present in the system. Now if the CPID of the coprocessor matches with one of the IDs, then that processor, suppose you assume that instruction which is being executed, which has come to the execute stage, has a CPID 1. Okay. In that case, what happens? This guy will pick up the coprocessor 1 will pick it up. Assume that the coprocessor is not busy with the previous instruction. Okay, it is first time it is encountering its own instruction. Now it will say that I am not busy. That means what? They will make this will be 0. Okay, this signal will be 0 because it is not busy now. And then is it absent? No, it is actually present. So it will make this as 0. Both of them it will make it 0. Whereas other coprocessor may decide not to even drive this signal. Okay, or even if it drives, what happens? It's an AND gate. So one of them driving it to 0 will make this output as 0. Agree? So once this processor has picked it up, and others are saying that no, I am not. No, I am not the right person to use this. So it will not say that I am interested in executing this instruction. Whereas only this coprocessor will say that I am interested in executing, but I can do it because the CPID of this matches with mine. That means what? Each coprocessor has its own ID embedded into the processor. Okay, it may be some hardwired ID. So this will have 2 in it, it will have 1 in it, and maybe we will assume that this is 3. So only when it encounters a coprocessor instruction with its own CPID as matches with its own ID 1 or 0, 1 or 2 or whatever. So it will pick up, and then based on that it will drive the signal. And I am not busy now. Okay, and then I am not absent, I am present. That means it will write as 0 there. Then ARM core knows that okay, I said that there is a coprocessor instruction I encountered in the execute stage, and any of you are willing to take it, and I am getting a signal back from one of the coprocessors that they are it is ready to execute it. Please remember, these coprocessors cannot have a common ID. They need to be unique. Otherwise, two people will say that I am taking it. Okay, that will be a confusion. So, as a system designer, ARM along with ARM, when they are putting the coprocessors inside the system, they have to make sure that each of the ARM the coprocessors have a unique ID, and then if the matching instruction come on the line, they will pick it up and then they will inform the ARM core. Now the question is, ARM, what does it do? Once the instruction is fetched or accepted by the coprocessor, it will not wait for that to be executed. Okay, because if it waits for that, what is the advantage of having a coprocessor? It doesn't make sense at all, right? Suppose I am asking for a coprocessor to be there in the system to speed up the whole functions, right? I want to ARM processor not to be blocked by any floating point operations or any DSP operation or network processor operation. But if the ARM core is also waiting for them to complete, then we are not adding any value there. Doesn't make sense at all for ARM core to wait for this execution to be completed. So as soon as one of the coprocessors say that I am interested in taking it up and then informs the processor ARM core back, then ARM moves that instruction out of the execute stage. Okay, that coprocessor instruction moves out of the execute stage and the next decode instruction comes into the execute stage. So once the instruction is handed over to somebody, it goes on. The ARM core just goes on with its own job. It doesn't care about what the coprocessor does with it. Then you may wonder, how can I tie up these two, because these are a common application. We'll talk about that later. Okay. At this moment, remember, once the coprocessor instruction is picked up by somebody, ARM core carries on with its own job. That means it will take the next instruction, and if it happens to be ARM instruction, it can execute, right? It is not tied to this instruction being executed, because if suppose there is no link between these two for a moment, then this instruction can carry on. So what is the advantage we are getting here? ARM is executing its own instruction, and in parallel coprocessor is also executing its own instruction, and you can have multiple coprocessor instructions in the sequence, and all of them are loaded with all those instructions they are executing. You can see that whole lot of things happening at the same time. Coprocessors are doing its own job and ARM is also doing its own job. That is the advantage of having a coprocessor. So unless this option is there, you won't get the benefit of it. But you may wonder, why is that control of fetching the instruction and then handing over to coprocessors are given to ARM? Because there should be one master, okay, one master and multiple slaves. A stable system should have one master and multiple slaves. There can't be multiple masters. So ARM is the master here. So the control of fetching the instruction from the memory is with this core, whereas executing a particular specialized instructions or the knowledge of that and then the special functions are built into this coprocessor and they do the job. Okay, so you can understand this now, I hope. See, one ARM instruction followed by a coprocessor 1 instruction followed by coprocessor 2 instruction, okay, and then another ARM instruction and followed by a CP3 instruction, then ARM instruction. What happens now at this moment? Okay, this is going on, this is going on, this is also going on, and ARM is ahead with the another instruction which is in the execute stage now. Now you can see that 4 instructions are getting executed simultaneously. Understand that? So that is what is happening here. Okay, good. I hope this is clear to you. So this is how the signals are sent back to it. Now we'll give the details of busy and why are we having this busy signal. We'll see that. Before that, I will explain you other control signals which are connected to the coprocessor. M clock, which is the main clock, and n wait is what? This is to delay the clock. Suppose there is a slower peripheral or memory, we want to delay it. And reset, please. Reset is not only going to ARM core, okay, it also goes to coprocessors, because coprocessor is executing something along with ARM. If reset is given to only ARM and not to CP, then the coprocessor will not know that there is a reset given. So this reset signal has to be given to all of them. Okay, then okay, so reset is given. It means it is the coprocessor also looks at the reset signal. Now what are these signals? Let us see one by one. So the signals used to interface the ARM with the coprocessor are grouped into 4 categories. Now what are these 2 signals? We have seen it earlier, memory request and sequential. So if you recall, we have seen about 4 different cycles where ARM core can be in. What are they? Non-sequential cycle, sequential cycle, internal cycle and coprocessor cycle. So whenever ARM encounters a coprocessor instruction, it is in a coprocessor cycle. If it is executing a coprocessor instruction, it is in coprocessor cycle. Otherwise, it is a sequential or non-sequential memory access, or it is something it is doing internally, doing some register transfer or something. So the coprocessor also should see all these cycles. Okay, and then what is this? This we will talk about it later. Okay, but at least know that there is a this signal indicates that if it is a low, it is a user mode, otherwise it is a privilege mode. So a coprocessor may be programmed to execute some instruction only when the ARM is in a privileged mode. Okay, it may ignore the instruction if it is given by the user mode. Okay, there is a possibility you can build a system like that. In that case, the CP2 has a signal entrant. If it is not in privilege mode, it may ignore the instruction. Okay, there are some control. Okay, for control purposes. Okay, what is NOPC? It is a opcode. So N means it's a low signal is active, low active. Okay, so code fetch is low. When the signal is low, it is the see. Oh, I'll tell you one. ARM core is there. ARM. This is ARM. This is CP1, coprocessor 1. I told you that the data bus is connected to both of them. Now inside the data bus, what is going on? Okay, it is the address bus. This is memory. Okay, memory is connected to. Okay, now what is going on in the data bus could be instruction or a data. So as a coprocessor, it should know whether it is what is going on in the database is an instruction or a data. So opcode is being read by the ARM core, or it is some memory cycle. ARM may be doing some LDM or LDR. It may be executing its own memory addresses. So to know that, it will look into the NOPC signal and then find out that okay, if it is low, that means an instruction is getting gets fetched. So I should take that instruction into the pipeline. The coprocessor will know that okay, it has to fetch the instruction into the pipeline. So that is why this signal is also important for the coprocessors to look at. Now what is T bit? T bit will be low when it is ARM is in thumb state. So what is the difference between ARM state and thumb state? The 16-bit instruction or 32-bit instruction. So if ARM is in thumb state, it is fetching a 16-bit instruction from the memory. So whereas coprocessor instructions are always 32-bit. So when 16-bit instructions are going on the data bus, coprocessors just ignore it. Okay, because they can't make any sense out of 16-bit instruction. As long as the ARM is in thumb state, ARM is not going to give any coprocessor instructions. Okay, the NCPI signal will not be activated at all because coprocessor instruction are always 32-bit. So it cannot appear along with the thumb state instruction. So effectively, if you are writing a thumb state code, you can't embed the floating point instructions along with it, because you will be mixing 16-bit instruction with the 32-bit instruction, which is not valid. Okay, so that is why coprocessor instruction and coprocessor instruction can appear or can be embedded along with ARM instruction, but not with the thumb instruction. Please remember this very important point. Okay, very good. These signals I already explained to you, and this is the data bus. It could be one of them will be selected and it will be there. Okay. Now let us understand how the different signal combinations mean what. See, when both of them, the coprocessor absent. Okay, let me use some other color here to bring out monotony. Okay, CPA, CPB, A means it's not available or something, it is absent. Coprocessor is absent is 0 means it is there present, and CPB it is not busy. Okay, CPB is 0 means the signal is 0, that means it is not busy, that means coprocessor is present and not busy. Okay, that means it can take up this instruction and it can execute it. Okay, you can read this thing, I will not go through this. So ARM ignores the instruction, coprocessor picks up the instruction. Now what is this combination? Coprocessor is there, but it is busy. What does it mean? It is busy with the previous instruction. I will give you an example. Suppose ARM instruction is there, after that some F add is there, floating point add, and immediately you are giving a F multiply. Okay, and then some ARM instruction. Now I told you any floating point operation may take more time, more cycles. Now FAD is in the execute stage and ARM has handed over to the floating point processor because it has set the 0 0, so it is now executing add now. Floating point add, it is executing the floating point processor. Now immediately followed by that is FML is coming. Now ARM processor, what it will do? It will hand over this FML also to somebody, right? So it will say that, hey, any takers are there for this. Now there cannot be two floating point processor. There can be only one because CP will be the same, right? So one coprocessor instruction or coprocessor will be there, which is the floating point processor. So it is already busy with the add instruction. Now it cannot take multi instruction until it completes this. So what happens? Because it is busy with FAD, FML cannot be taken, which happens to be in the next instruction itself. Now what happens is, because of that, the ARM pipeline stalls. It stalls. Okay, I will tell you why. This is the ARM pipeline. Okay, this is the fetch, this is decode, and this is execute. Now there is a coprocessor. Okay, floating point processor. It has got a fetch, decode, and execute. Now add instruction is here. Mull also has been read by the coprocessor. Okay, floating point coprocessor has already read the mull instruction, but it cannot see. Typically these two instructions are to be handed over, not handled by this processor only. Okay, but it is already executing this in its own pipeline. Okay, so it cannot execute this instruction now. So we have this instruction has to wait. Now what happens here? Here first add came. This FAD is handed over to this guy. Now FMUL was here, right? Previously FMUL was there. Now that is picked up by now because add has come here, FMUL will come here now. Okay. After that, here some ARM instruction is sitting there, as you assume. Now FML is to be taken over by the again same coprocessor, but it cannot take it up because this is going on. It may take maybe a 4 or 5 cycles or 6 cycles, assume. Now until this instruction is taken over by this guy, the pipeline stalls. ARM pipeline, okay, stalls. You may wonder why should it stall now? Earlier for FAD it doesn't stall, it carries forward, whereas for FML it is waiting. The reason being, there is a coprocessor to take over this FML because CPA is 0. That means it is not absent. No floating point coprocessor is present, but CPB is 1. That means it is busy. So that means there is a guy who can take care of this instruction, but it is busy with his previous instruction. So now ARM has to wait. If it doesn't wait, what will happen? This FML will go out of the pipeline and then it cannot keep track of the flow. Okay, because I told you that ARM is the master and others are slaves. So the master has to make sure that the control flow is properly maintained. Okay, but you may wonder why in FAD it went ahead. It went ahead with FAD because somebody has taken over the instruction and it doesn't want to wait for it. So as a typical programmer, if you are a smart programmer, okay, you should not put two instructions belonging to the same coprocessor one after the other. Then you are unnecessarily stalling the pipeline of the ARM core. Suppose if there is something else that to be done by ARM before the FML has to be done, then those instructions can be put here instead of FML, and then you can put FML later. Now what happens during this gap, while ARM is busy with its own instruction, FAD also would have been done by the CP, and it is now no longer busy when the FML comes into the flow. Then FML will be taken over by coprocessor. So that is the kind of mixing we have to do. A floating point instructions and the ARM instruction needs to be mixed properly so that you make use of the gaps in between for the ARM core to go with its own execution without waiting for the coprocessor to complete it. So it is left with it is left to the developer programmer to make use of this particular combination. Okay, then only you will be using the taking the advantage of the coprocessor. Now, why this is invalid? It says, okay, coprocessor is absent. That means what? No takers for this particular processor instruction, coprocessor instruction. But somebody in the coprocessor list says that I am not busy. See, it is a contradiction. Okay, that means it says that it says that I cannot execute this instruction, but I am not busy. So it's a bad combination to happen. Suppose, see, there are two coprocessors, okay, CP1 and CP2. Okay, both of them saw the instruction which had a coprocessor ID 3. Okay, assume that in the system only these two are there. Okay, both of them say, okay, this is not for me. So that means they wouldn't have driven the CPA to 0. It will maintain it as 1 only, because it is not going to take up this instruction at all. Okay, so as far as this instruction is concerned, the coprocessor is not present in the system, and they should also drive the CPB1 to say that okay, I am busy. Okay, so it will not confuse the processor. So this is not a kind of a valid response. It cannot say I am not busy but I can't take this instruction. So that's a bad combination. So that's why I am saying that this combination will not happen. Okay, no coprocessor will see this signal is a AND of multiple coprocessors giving. So nobody should have made the particular signal 0 in this combination. If this happens to be 1, this also should be 1. Now what happens? This is a valid combination because no takers for this coprocessor instruction, and all of them are no, whether they are busy or not, they say that no, I cannot take this instruction at all. Now what does the processor do? Let us see. Okay, let me use blue color for a change, or maybe brown. Okay, now ARM core. Okay, this is fetch, decode, execute. It found that there is a coprocessor instruction with a CP, maybe CP ID, coprocessor ID as 5, but in the system there are okay 3 coprocessors which ID 1, 2, 3. Now as soon as it sees this, ARM core would have sent a NCPI signal. Okay, coprocessor instruction. Any takers for this? It would have made this low. Okay. Now this guy also will say I cannot take it, I can't take it because it's a coprocessor 5 instruction. Now what does the processor do? That's a valid question to ask. See, it cannot solve the pipeline because there is no takers for this particular instruction. If there is a taker, that person would have said that I am busy now but I am present. That means the CPA will be 0 and CPB okay would have become 1. Then it can wait because there is somebody who can recognize this instruction, but it is currently busy, so he may take it up later. But when they say that no, it is busy as well as I am not the guy to recognize this instruction, that means what? No takers for this currently in the system. Then ARM has to do its own job. What it will do? It will generate an undefined instruction exception. Okay, you might you heard about this undef instruction, right? Exception. It will go to that instruction exception, and that handler needs to do the job of what to do with this instruction. Okay, now you may wonder why are we supporting both? See, as a system designer, I may decide to have a coprocessor in hardware, or I may decide to do a simulation using it in software. Suppose the floating point operations can be done in software also. So I may emulate the software in the software. So in that case, it should be executed in the handler. Okay. So that instruction needs to be handled by some left untouched. Okay. So hello. Okay. Hope you have understood this combination of various things. So if a particular instruction is not recognized by any coprocessor, then ARM generates an undefined instruction exception, and it is taken care of by the software. So if we decide that I don't want to have a hardware coprocessor and then I can handle it in software, that option is available. Okay. So if no takers are there for a particular coprocessor instruction, that we can do undefined instruction trap and then execute whatever is supposed to be done by a coprocessor in software. So only thing is, what do we lose here? The parallelism, because ARM is performing the job of handling the particular coprocessor instruction. So it is going to affect the performance, and there is no hardware which is running parallelly along with ARM executing the coprocessor instruction. So it will be pretty slow. But the thing is, we don't need extra hardware, we don't need that extra power and no area, but it is okay if we can handle it in software, it can be done. So a particular instruction, if it is not picked up by the coprocessor, then ARM generates an exception to handle it. Okay, very good. Now let us see. So the ARM process evaluates the type as well as the condition code and then decides whether to be executed or not by a coprocessor. Okay, I told you about EQ and NE and all those control signals. If a particular coprocessor instruction doesn't have to be executed because the condition code failed, then it will not generate the signal. That means the coprocessor also will ignore that instruction. Now I told you that ARM is connected to the address bus, not the coprocessors. So coprocessors are not connected to the address bus. So ARM only will generate the addresses required for the instruction fetch, as well as if there are any instruction, a floating point or a coprocessor instruction needs a memory access, that is also generated. The address is generated by ARM. These coprocessors cannot generate any address because they are not even connected to the address bus. So they can't access the memory directly. They have to go through the core only. So ARM takes the undefined instruction track if no coprocessor accepts the instruction. That means, how does it know? Both CPA and CPB happens to be 1. That means there is no coprocessor which is present, and there is nobody who can take this instruction. So that means it has to be handled by ARM only. So it will generate a trap or that undefined instruction. So at the same time, what does the coprocessor do? It decodes all the instructions to determine whether it can accept the instruction or not. It ignores if the instruction does not belong to it. Okay. That means what? If an instruction is an ARM instruction, it will ignore. If the CPID doesn't match, that means what? This coprocessor instruction doesn't belong to it. It may be for some other coprocessor. So only one coprocessor whose ID matches with this ID in the instruction will say that I am taking up this instruction. So otherwise it is ignored. So that's the logic used. Now indicates where it can accept the instruction by using, okay, the coprocessor indicates whether it can accept or not using CPA and CPB. When the instruction is in execute stage and the NCPA is made low by ARM, please remember, it should be in execute stage and this should have been low. If it is not low, what does it mean? The ARM decided that condition code is failed. That means what? The F add EQ was the instruction, and 0 flag in the ARM core is not equal to 1. That means this instruction should not be executed because EQ condition is not satisfied. So please remember, this condition code is maintained in ARM core, not in the floating point process. It may also maintain, the coprocessor also maintains the status and other things, but condition codes that are mentioned in the instructions are maintained in the, or with respect to the CZNV flag in the ARM core. Okay, you may wonder why the CZNV of ARM is used, because the decision on whether to execute an instruction or not, okay, is with the ARM core. He is the master. ARM is the master. So it can do only based on its own flags. It cannot take a decision based on the flags in other coprocessor. So the conditions are all to do with the something in the CZNV flags of the ARM processor. Okay, so that's how the design is, because that is the only possible design is in the scenario, right? So because one guy has to decide the control flow of the whole program, that is ARM core. So coprocessor fetches any values required from its own register bank as mentioned by the instruction. So once the coprocessor instruction is picked up by the processor, then it will look at the opcodes of. So these opcodes will be most probably for some of the operations to be done by the CP. It will be its own registers. Okay, I told you that the coprocessor also has its own register set. So the opcode operands may be from those register files. So here FAD, suppose it mentions that okay, you perform a floating point arithmetic using those registers inside the processor. Maybe you call that F1 and F2, these registers, and then put the result in F3. Then it can add the values in F1 and F2 and then put the value in F3, which is inside the CP. Okay, inside the coprocessor. So the instructions may fetch the operands within the coprocessor registers and perform the operation required by the instruction. Good. Okay, what happens to unaccepted instruction? If a coprocessor cannot execute an instruction, that is no coprocessor in the system responds with an acceptance of the instruction. ARM generates an undefined instruction. I told you this. Programmer can choose whether to emulate the coprocessor function in software by writing undefined instruction exception. I told you this also. Since a dedicated hardware coprocessor is not integrated with the ARM core to handle the instruction. Okay, if it is not there, hardware is not there, then it has to be done by the software. You can't say I will put a coprocessor instruction in the instruction stream, but I won't handle it. I know the system doesn't have a hardware. Then what happens to that instruction? ARM cannot do anything with that, and then there is no coprocessor also who can execute it. Then what will happen? Your program will fail. So we cannot have that condition at all. So if suppose you know that there is no coprocessor which can take that instruction, we have to support that coprocessor instruction by writing the exception handler properly, undefined instruction exception properly to handle that instruction. So okay, what is coprocessor ID? Up to 16 coprocessor can be referenced by a system with a unique coprocessor ID number to identify it. Please remember, in a system, in a SOC, in a system, ARM is there, and then there are CP1, CP2, CP3 are there. They need to be unique. Okay, they can't be CP1 and CP1, two hardware coprocessors which are having the same ID. It's a cause of failure. Okay, that is a bad design and it can't be done. Now there are some coprocessor ID which are reserved. Okay, one is a debug communication channel processor. I will talk about that when we touch upon the debug module of ARM. So that is debug controller, and then reserved one is 13 to 8. That means ARM has reserved these numbers. So only these are available for users. That means what? If you are a hardware designer and you are building a coprocessor, you can use that only 7 to 4. If suppose you are using with the ARM 7. Okay, I am not talking about the later processor, family processor. We are only concerned about ARM 7 in this course. So we are talking about what are the registered coprocessor IDs supported by ARM 7. There are 16 coprocessor IDs, and then out of which 13 and 8 are reserved, and these are all reserved special purpose, and this is also reserved. So you are only having only these 4, 5, 6, 7 only, which you can develop your own processor. Now you may wonder where the floating point coprocessor is. It is actually inside this. 10 and 11 are used for that. We will talk about that later. Okay, so this is debug and this is system control. There is another coprocessor which is called system control. I'll touch upon that later some point in time. Okay, so these are different IDs which are reserved for different purposes. That's all. So this will be mentioned along with the instruction. Okay, I will talk about the instruction format in the next session, so you will understand that. So pipeline following, I talked about this. So for a completeness sake, I have put it in the slide. Every coprocessor in the system, okay, must contain a pipeline follower to track the instructions in the ARM processor pipeline. So okay, coprocessor connect to the configured ARM data bus as well as this signal. This you know already. It is essential that two pipelines remain in step. But that means what? The coprocessor pipeline and ARM pipeline, they should be in step. In step means they should be in synchronization, because when a particular instruction moves from one stage to the other stage in the ARM pipeline, same transition happens in the coprocessor pipeline also. Not only in one coprocessor, if n number of coprocessors there, all of them will transition. The instruction will transition to next stage. So you may wonder how is it done, because M clock is common anyway, right? All of them are connected to M clock. So and then they are also having N OPC and other signals which are seen by both ARM as well as the coprocessor, so they can be in sync with each other. And flushing and refilling of ARM pipeline, when will it happen? Suppose ARM is executing a branch with a link or branch instruction. What happens to the pipeline? It gets flushed. But what happens to the coprocessor pipeline? They also get flushed. Okay, so it is like they mimic what the ARM does. All the coprocessors are dancing to the tunes of ARM. So whatever this guy ARM does, the coprocessors also will do, because then only they can be in sync in terms of pipeline. There are no coprocessor instructions in the thumb instruction set. I told you this. So coprocessor must monitor the state of T bit, because T bit will be low when it is in thumb state. That means during thumb state, coprocessor will just ignore what is happening on the bus. It will only monitor the T bit and then it can just sleep. It doesn't have to do anything, because it doesn't have to carry the thumb instruction inside the pipeline at all, because anyway it's not going to encounter any coprocessor instruction along with thumb instruction, right? Because thumb instruction means 16-bit instruction. There cannot be one odd man out 32-bit instruction between them. So it's very safe for the coprocessor to just sleep when there is a thumb mode, in thumb mode. Okay, so the coprocessor decodes the instruction currently in decode stage. If pipeline of its pipeline to check whether it belongs to it. If the coprocessor number matches with that own ID, it will generate the required signal. If the instruction currently in decode stage is a relevant coprocessor instruction, suppose, okay, coprocessor is just looking at the instruction and then it sees that this is a coprocessor pipeline and it is in the decode stage. This pipeline the coprocessor ID matches this own ID. Okay, this is CP1 and the instruction also ID is 1. Now what does it do? The coprocessor attempts to execute the instruction. It will start executing the instruction. Okay. So you may wonder why is it starting the execution? Because typically coprocessor instructions are going to take more time, and most of the instructions are internal to its own registers, right? So it knows that the ID matches, okay, and it belongs to it, and it is not busy, okay. So it will move that instruction maybe along, it will move only when the ARM moves to the execute state, but it will start executing it little ahead, okay, just to keep save some few cycles. Okay, it may execute the instruction ahead, but wait a minute, let me erase it. The coprocessor handshakes with the ARM core using the CPA and CPB. It will inform the ARM core saying that, hey, I am taking this instruction. Okay, CPA, CPB, both will be 0. Okay, that means what? It is taking the instruction. But please remember the NCPA instruction, that signal from ARM. This is ARM and this is coprocessor here. Okay, that has not come. NCPA has not come because ARM may be busy with its own instruction. Okay, but let me explain this little bit. Hope you will understand it. See, this is coprocessor instruction is there in the ARM core, and same coprocessor instruction is there in the coprocessor also. Okay, it is in decode stage, but it starts executing. Coprocessor has identified that this instruction belongs to me, and I am not busy now, so I can start executing it. But it will not write the result into the register file. Okay, anything, suppose it is computing some addition or something, until it gets a NCPA signal from the NCPA signal. Okay, from the ARM core. Why? Because there is a possibility that there is a branch which has happened and this was never executed to be executed at all. In that case, even ARM, the coprocessor also should not execute it. Or there is a possibility that condition code has failed, that EQ condition or some other condition code has failed. Then also that instruction should not be executed. So, but I said that the coprocessor starts executing it. But if it doesn't write the result into the register file, then it is as good as not executing, right? It might have done some job, but it may ignore it. Whatever it has done in between, it will drop everything and then it will start fresh. So the value which is status, what is maintained by the registers in the take an example, it's a floating point process. It is not affected by this instruction because ARM decided that this instruction should not be executed. So I hope this is clear to you. So coprocessor handshakes with the, it informs the ARM core that I am taking it, okay, as soon as it decodes it, but it does not have to wait for NCPA to be low, but it must not commit the result until this becomes low. It should not commit the result, okay. Good. So same thing, I think I have explained it already. So this quiz doesn't have anything, but I want you to take a 2-minute break to look at these questions and options and then see which are the options are correct. There may be multiple options, but I am just giving you, try to look at it and then come back. Welcome back. If all the options look correct to you, there is something wrong. Okay, only the C option is right. That means condition codes might have failed, so the coprocessor instruction should not be executed. I am saying branch also another option, but are these options are valid? Let me go one by one. The coprocessor instruction being executed may not be valid. See, a coprocessor has already started the instruction means the ID was matching, that's why it has started executing. Then this is no longer true, right? It cannot be that the instruction cannot be invalid instruction because some coprocessor has picked it up. That's why it is going ahead with execution, but it is waiting for NCPI to become low to commit the result. That means this is not correct. Then is it correct? ARM might have decided to take undefined instruction exception for the instruction execution at coprocessor. This is also not true. Why? The processor, once a coprocessor has taken up the instruction, it will say that CPA and CPB, it will make it, see, it is executing it ahead, but it would have made this both 0. That means what? It says that I am taking this instruction, I have this is valid instruction ID, so I am taking it. Somebody has told. Then after hearing from the coprocessor that somebody is ready to execute it, the ARM core cannot decide to take an exception. That is not correct. Okay, only when no coprocessor is ready to execute the instruction, it should take the exception. Otherwise, this is not a valid option. Okay, can this be a valid option? Some other coprocessor might have also responded to the same instruction by driving CPA, CPB low. Is it true? I told you that CPA IDs are unique. If another coprocessor is also driving the signal, even ARM may not even know that because it's an AND gate. Okay, I'm sorry about the AND. Okay, it's an AND gate. If 2-3 coprocessors are driving it as 0, CPA and CPB, it will not even know. So, and is that possible? It should not be. In a system, you cannot have a coprocessor with the same ID. So that is why only this is correct answer. Okay. So execution of the coprocessor instruction. Coprocessor instructions progress down the ARM core. A coprocessor instruction is executed if the following are true. That means coprocessor instruction has reached the execute stage, and then ARM processor cannot execute the instruction because it's the coprocessor instruction and it is a part of the undefined part of the instruction set, and the instruction has passed the conditional execution test, and CPI is low, and CPA CPBS or somebody has accepted this, and then the coprocessor can commit the instruction to execution. Okay, that's all. I hope the whole thing is clear to you guys. So we have not told so far what are those coprocessor instructions. Okay, I only said some coprocessor instruction, maybe FPAD and some floating point. I took an example. We will see what are the instructions supported and then what all can be done using those instructions in the next section. But now I hope you understood that how ARM is reading the instruction and then handing it over to coprocessor, and how that coprocessor execute them. Okay, if you have understood this and how they communicate with each other, then I think we have done the job of today's class. Okay, so happy talking to you. Thank you very much for your attention. See you in the next class. Have a nice day. Bye bye.